Hello everyone, I'm Dreamin' on Latios. If you haven't heard that name before, I'm a hobbyist game developer and creator of Latios Framework for Unity Dots. So a number of people have expressed interest in this framework to me, but found the documentation and features a little intimidating. So I decided to make this video to help make this tech a little more accessible. If you haven't heard of Unity Dots before, it is bleeding edge, unfinished technology that I'm not even going to try to explain. It is not for everyone. And no, the Latios framework does not make dots any easier to learn, but it may make it easier to work with. If you know what these things are, give it a shot. You may be surprised. So with that out of the way, let's get into it. As of version 0.3, the Latios framework is composed of 3 modules. First is core, and it mostly solves problems and annoyances I encounter when working with dots. Second is SciShock physics. This one is still really early in development and is more of a spatial query engine than a physics engine, so I can only really recommend it if your game has lots of triggers or distance queries or something. But it has a pay-for-what-you-use model, so its existence won't have any performance impact if you decide to use Unity or Havoc physics instead. And lastly, we have Miri Audio, which is an out-of-the-box, pure ECS audio solution. It is built on top of DSP Graph and has things like voice combining and 3D spatialization. And since this is dots, it totally scales. Anyways, enough intro, time for some examples. So a really common misconception is that Latios framework is incompatible with Unity physics, so let's install the framework into the Unity physics samples. I'm using the Git URL here for simplicity, but you can also find the framework on OpenUPM, if that's your thing. Alright, now that the package has been added, we need to install the extensions into the ECS world. Easiest way to do that is to right-click, create, Latios, Bootstrap injection workflow. This creates an iCustom Bootstrap, which is a lesser-known Unity feature for customizing the default world. And with that, let's enter play mode and check that everything is working. Looks like it. Now, is it just me, or is this demo boringly quiet? Let's add some jams to liven things up. First, we'll add a Miri audio listener to our camera entity. Then we'll find our bullets and add a Miri audio source. We can drag in our jam and turn on looping, and maybe turn the volume down, since we'll have a few of these. The voices parameter tells us how many unique sounds to play for all looping sources using the same clip. The rest get automatically combined. Let's set this to 5. We'll also increase the lifetime, because that sounds more fun. For our next demo, let's make a really simple movement game where the player moves around on a 2D plane. If they touch a red thing, they die and the level restarts. But if they touch the green thing, they move on to the next level. A common way to do this is using scenes. However, if you try to do this using scenes and dots, weird stuff happens. The entities from our old scene are sticking around with the new ones. We can make them go away with the Latios framework. All we have to do is add a request load scene component to any entity and specify the scene name we wish to switch to. Look at that! It works! But there's still a few problems. Because we are using Entity Manager to add the request load scene component, we now have a sync point and our for each is not using burst. And all of this is on the main thread. We can solve the main thread issue by storing the player in a native reference, and the other issues can be solved by using an entity command buffer. And it's still working. But is it just me, or is that way too much boilerplate? We can fix that by using the Latios framework version of System Base, which is called Subsystem. A subsystem has all the features of System Base, so simply changing the type does not break our code. See? Still working. But now we have access to new special features. We won't be needing this block anymore, and we'll instead get our NAD command buffer from latiosworld.syncPoint. We don't need this line anymore either, the subsystem automatically handles that. And now our code only has one more line than when using Entity Manager. But does it work? Yup. There's a couple other things we can do with scenes. We can prevent an entity from being destroyed using the Don't Destroy on Scene Change tag. We can also get some useful info from the scene manager using the current scene component. This lives on a special entity called the World Blackboard entity, which has some convenient API shorthands. Here we'll print the previous scene and current scene on the first frame since the new scene loaded. Let's add a death counter to a game. We'll add a component type, then we'll set up our canvas and create authoring scripts in a UI system. I guess now is a good time to talk about Blackboard entities. If you've ever used the ECS singletons, you know that the API is very convenient. However, singletons eat up a lot of memory, cause systems to run unnecessarily, and throw a fit if you ever try to load a scene with an authored instance for the second time. Blackboard entities solve all these problems. There are two Blackboard entities, world and scene. The scene entity is recreated whenever the scene changes, while the world entity is left alone. To specify we want a game object's authoring components to be added to a Blackboard entity, we need to add Latios, core, Blackboard entity data. The death count needs to persist between scenes, so we'll target the world Blackboard entity. We will set the merge method to keep existing. This means that when the scene loads, if the world Blackboard entity already has a death counter, it will use the old value instead of the new one. We can read the value in the same way we log the current scene, but the world Blackboard entity is a property of the system and using Entity Manager under the hood, so we can't use its convenience methods inside of a job. Instead, we assign it to a local entity and use setComponent. Our count now increments and persists between scenes. Just for fun, let's go to level 2 and change the merge method. Now our death count resets once we reach level 2. That's enough for this demo. Let's do something a little more advanced. This time, we'll make a turn-based strategy game played on a grid. For each turn, all players choose an action. Then all the actions are played out at once, with the priority of the actions being dependent on the action type. We'll have a system for each action, and so our system order is what determines the action priorities. That's something we'll probably want to experiment with, which can be a little cumbersome with attribute-based ordering. Fortunately, there's another way to control system order using the Latios Framework. We can enable it by creating a Latios Bootstrap explicit workflow. With this bootstrap, only Unity systems, core systems, and a special type called root supersystems are added by default. What are root supersystems? Well, you know how Latios Framework has a special subclass of system base called subsystem? It also has a subclass of component system group called supersystem, and root supersystem is just a subclass of that. We'll make a new file called supersystems.cs and create a root supersystem called gameplay root supersystem. We'll also make two supersystems called per frame supersystem and per turn supersystem. We can specify the systems and order they execute by overriding create systems and making sequential calls to get or create and add system. We'll first add per frame supersystem. This is where we will handle player input and game loading. Then we'll add per turn supersystem. Because gameplay root supersystem will be injected, we use attribute ordering to order it relative to the Unity systems. Let's enter play mode and make sure our system ordering is what we expect. Looks right to me. Let's build out our players, components, input, and UI. For this game, we'll start with only two types of actions, moving and attacking. Each action can be performed in one of 8 directions. If one player attacks another, that other player dies and is removed from the board. The last player left alive wins. Yes, this is a battle royale. Now that we have input, we need a mechanism for playing the turn only when the user presses input. We could use a singleton tag for this, but that requires a structural change. Ideally, we would like to pull a bool once for all the systems inside per turn supersystem. Fortunately, the Latios framework has a solution for this too. Supersystems and subsystems have an overridable method called shouldUpdateSystem. You can use this method to specify custom update criteria. This is logically ANDed with the default update behavior, so if you want full control, use the alwaysUpdateSystem attribute. Let's add a test system inside per turn supersystem to make sure this works. We're looking good so far. The next challenge is the grid itself. It would be nice to have a 2D array which the systems could all interact with. We could expose this on a system, but that requires systems to pass job handles back and forth. We also have an ownership problem. What if we have more than one algorithm that can generate our grid? Who do the other systems go to when they need grid access? We could instead give the ownership of the grid to an entity using a dynamic buffer. This gives us automatic dependency management, and combined with Blackboard entities, this also solves our ownership problem. However, we lose our ability to abstract away the internal memory of the 2D grid, and we're out of luck if we wanted to support infinite grids with a custom sparse container or something in the future. You can probably guess it by now, the Latios Framework has a solution to this problem too. However, this one has a little steeper learning curve. The solution is collection components. We can create one by implementing the iCollection component interface. Inside, we can create our native array and create our 2D abstraction. However, and this is the tricky part, this is not a real component. It is an imposter, and that follows the existence of a real component. We can define a tag component for it to follow, and then specify it as the associated component type. We also need to define a dispose method for it. Now that we have our grid component defined, we can create an instance and add it to our same Blackboard entity using this shorthand to an Entity Manager extension method. This will add the associated component and store our collection component instance in framework storage. We can now schedule a job or two to populate it with the authored players. Dependency management is fully automatic per instance, so this is all we have to do. You'll also notice the checkerboard tile generation logic is a little unusual. I'm using a command buffer here in order to assign the positions in burst. However, if I were to use an entity command buffer, each tile would be instantiated one by one, which is kinda slow. So instead, I'm using instantiate command buffer, which can dean or leave the tiles and batch instantiate them while still initializing the components correctly. Now that we have our grid, we are ready to implement some actions. Let's start with the attack system, since this one is easier. When we access our grid, we specify whether we want it to be read-only or read-write. As soon as we do this, subsystem's dependency property will automatically be updated to include previous job handles interacting with the grid. I'm using destroy command buffer here, which is similar to the instantiate command buffer I used earlier. This one is a little lighter weight, but otherwise equivalent to entity command buffer for this use case. Don't forget, we have to add our new systems to the supersystems. Let's try it out. When we attack an empty space, nothing happens, but when we attack the other player, bye! Move system is tricky, as we have to handle wall boundaries as well as collisions, but besides interacting with the grid, it isn't using any framework features. Now when we play, we see the other player move. If we attack where they move to, they don't die, but then if we attack the same spot again, they do die. This is problematic because it means that when two players are next to each other, their best option is to always attack each other and both die. That's not fun, so let's try swapping the action priorities by changing the system order. Now if we attack where the other player is standing, the other player dodges, but if we attack in front of them, they die. This is better, but it still is advantageous to campy players. We can fix this by giving attack priority to any player that tried to move the previous turn. But this video is about Latios Framework and we're already 13 minutes in, so try that on your own time, and let's move on. For the final demo, let's explore some features of SciShack physics and Miri audio. First, I'm making this shader graph which displays the base color, except it swaps white with rainbow. No symbolism here, I just like colorful animated things. Let's make some prefabs using the shader, and since we'll be playing with SciShack, we want these to have colliders. For the sphere, capsule, and cube, we can just use Unity Engine colliders, but for this weird thing, we want to treat all of its colliders as one. So for that, we'll add a Latios Physics Collider. Then we'll set the collider type to compound and enable generate colliders from children. SciShack does not currently do rigid body simulation, so we'll make our own linear and angular velocity components and a system to step them. We'll also make a couple of components for configuring the simulation, including a spawner and our world bounds. The world bounds will be added to the scene Blackboard entity. For our spawn system, we'll use an entity command buffer for instantiating our prefabs and destroying our spawners. Most of the values are pretty easy to randomize, but for scale, we also want to scale our colliders appropriately. The component type for any collider in SciShack is simply called collider. We can get a scale version of any collider by calling physics.scaleCollider. However, only box colliders can be scaled non-uniformly, so to figure out if our collider is a box collider, we can query its type. We can also cast a collider to a specific type implicitly, then modify its properties manually, and finally cast it back. To test our colliders out, let's write a simple system that draws the collider's bounding boxes in the scene view. We can do this easily using this method, which can be safely called from a burst job. But I'm an idiot and forgot to bump up the debug lines count in the Unity command line, so only some of the bounding boxes draw. Anyways, these things move, but they don't interact, so let's create a collide system to fix their ignorance. There's a function called distance between, which can test two colliders against each other. So we could test every collider against every other collider, but that's really slow. Don't do that. Most of the colliders aren't even close to each other, and we can be clever about that to speed things up. SciShock has one such clever algorithm already implemented called FindPairs, but its input requires a collision layer and something that implements an iFindPairs processor interface. Let's start with getting the collision layer first. A collision layer is a special acceleration structure in SciShock for fast spatial queries. We can get one using build collision layer. There are overloads that take raw arrays, but for our use case, we want to extract the data using an entity query. But that means we need an entity query. Have you ever wished you could create an entity query using the entities.forEach style Fluent syntax without actually having an entities.forEach job? Maybe it's just me, but I always found the manual way of creating entity queries overly verbose and a little inflexible. So to remedy this, there's this thing in subsystem called Fluent, which can be used to build entity queries using a Fluent API. We only read the angular velocity, so we set the read-only property to true. We also want to ensure that this entity query meets all the required criteria for build collision layer. So we use the extension method patch query for build collision layer. Yep, Fluent is a fully extendable API, and it even has special methods for automatically resolving conflicts. The last step is to call build to get the actual entity query. Now we can build our collision layer, which requires passing in the entity query and our system. Many things in SciShock also use a Fluent API, and build collision layer is one of them. So we can call 0 or more customization methods. I won't get into them in this video, but there's detailed documentation for them in the package documentation. To get our actual collision layer, we need to call a scheduling method, since this process uses jobs. That's one item down. The other item is the iFindPairs processor. The best way to think about iFindPairs processor is to pretend it is a job type, except the burst compile attribute is already applied. Just like other jobs, we can stuff containers in here along with their attributes, and we need to implement an execute method. FindPairs generates a result for each pair of colliders whose bounding boxes overlap. It is up to us to test that the colliders actually overlap, using the distance between method I mentioned earlier. The out parameter provides us some useful info to write this crude and janky separation logic, but we can also use it for other gameplay logic, like this color transferring mechanism. Our processor is defined, so the last step is to create an instance of it and pass it to our FindPairs algorithm. Just like build collision layer, FindPairs is also a Fluent API, so we get to choose a scheduling method for it. And don't forget we need to dispose our collision layer, just like any other native container. Let's try it out. This is what it looks like after a few seconds of colorful exchanges. However, it seems we got a single thread bottleneck. That's no good. Build collision layer has a schedule parallel method, and it kinda just works, so that's half our problem gone. FindPairs also has a parallel scheduler, but when we try to use it, we get errors trying to access component data from entity in parallel. That makes sense. The collider entities are random in memory, and an entity could be involved in more than one collision. FindPairs can't identify which pairs are unique from other pairs at any given point in the process. Except, it actually can. This may seem like some kind of magic, but FindPairs performs this tracking without any additional performance overhead. It's just a nice side effect to how the algorithm works. Entity A and Entity B of FindPairs result are actually a special type called safe entity, and they are each guaranteed to be unique to the thread for the entire duration of the execute method. All we have to do is prepend physics to our component data from entity types inside our processor. Hey, it's multi-threaded. The distribution isn't perfect, and we can still optimize it by messing with the settings, but that's too application dependent for this video. Instead, let's add some triggers which will be invisible and modify the colors of our main entities at a constant rate. We'll make a second entity query, a second collision layer, and a second iFindPairs processor. This time, we don't want to process pairs within one collision layer or the other. We want the pairs between the two. FindPairs has a mode for this called bipartite mode. When using this mode, we pass in two collision layers into FindPairs, and the order matters. Entity A in every result will always come from the first collision layer passed in. Entity B will always come from the second. With this in mind, our processor can make very aggressive assumptions as to which components each entity has. By now, you may have realized SciShock isn't intended to be a typical physics engine. Instead, it is designed to provide common physics algorithms which can tightly integrate into our game logic. But is it just me, or is this demo boringly quiet? It would be nice if we could have audio cues for when our colored entities crash into each other. Let's make a new game object and add a Miri audio source like we did in the first demo, except this time, we'll leave looping unchecked. We'll also leave the voices parameter alone since it doesn't do anything for non-looping sources, but we'll still turn the volume down. Because the converted entity's only behavior will be playing non-looping audio, we can check auto destroy on finish. In Miri, everything exhibits play on awake behavior, so the way we play audio clips is by either instantiating a prefab or adding the necessary components at runtime. Instantiation is usually faster though, so let's make this game object a prefab and make our collider prefabs reference it. Then we'll create 2 instantiate command buffers for spawning these audio sources. Non-looping sources are called one-shots, and they have a completely separate runtime component from their looped counterpart. This first instantiate command buffer will be responsible for creating the sound at the contact point. The other instantiate command buffer will be used for sounds emitted by the 2 collider entities and follow them after the collision. So for these, we will be setting a parent component. We also need to ensure that the new entities have a local to parent component, but we don't need to set the value, and so we call addComponent tag instead. For initializing our audio source, we'll copy the version from the prefab as a base. We can modify several parameters, such as the falloff controls and the volume. But wait, this is a parallel job, and our instantiate command buffer requires a sort key. That's easy though, because our findPairs result has a job index field precisely for this purpose. The final thing to do is to add a controllable camera with an audio listener, and then fly through the chaos. And that's all the demos I have for this video. Hopefully they're helpful. There are links in the video description to both the framework and the demos from this video. There's also a link to LSSS, which is the open source project on screen in front of you. It showcases many of the functionalities of Latios Framework demonstrated in this video, as well as some more advanced usages. I sometimes get asked if I have any long-term plans or goals with the framework, and the answer is yes. It looks like this. I have a lot of tech planned for the framework, but at the rate I'm going, it may take me a few years before I even begin development on the artistic projects. But fortunately, there's a few magic buttons you can press to help me out. The first 2 are the lamest. I think they do something, but I'm not really sure. Click them if you feel like it, I guess. This button is actually useful. Lets you ask for more videos, and maybe live streams or something. Don't expect another video like this though. This took way too long to make. The next 2 are even more powerful. You can request features, report bugs, ask technical questions, provide suggestions for improvements, or even discover which areas of the framework you can help improve, if you got the time, because I don't. And lastly, there's one button that you should never, ever press. It's this button. But seriously, why is this button so taboo? Half the people who press it start off apologizing for bothering me. Please don't worry. This is the best button if you don't want to ask a question publicly. One of the most time-consuming parts of developing the Latios framework is coming up with projects to battle test new features. So I'm quite open to collaborative projects or game jams. I also get a lot of motivation from interacting with the DOS community. So if you want to ask me about any future projects or the history behind my username, that's cool too. So to summarize, lame buttons, video requests, and memes I guess, questions and feedback, and talk about anything. Now go check out the repos in the description and hit those magic buttons, and I'm going to write some more code. Finally.